In this video, I will derive the rotational energy of a system that consists of a large number of linear molecules such as HCl or H2, given its partition function. Assuming the Boltzmann distribution, the total energy of a large number of particles can be expressed in terms of its partition function. E equals -n times dlnq over d beta. E is the total energy, n is the number of particles, q is the partition function, beta is 1 over kBt. The energy can also be expressed in terms of the temperature of the system. It's n times kBt squared times dlnq over dt. And q can be translation energy, or rotation energy, or vibration energy, or electronic energy, or the product of these four partition functions. And if you plug in the product of these four partition functions in this equation, it will become the sum of four natural logarithms of these four partition functions, and therefore energy is additive. The total energy equals the translation energy plus the rotation energy plus the vibration energy plus the electronic energy. Today we're focused on the rotation energy of a linear molecule. The rotational energy levels of a linear molecule are J times J plus 1 times h bar squared over 2I. H bar is the reduced constant, I is the moment of inertia, and J can be from 0, 1, 2, 3, and so on. The degeneracy of the jth energy level is 2J plus 1. Again, J is the vector of the angular momentum of the rotation, and its z component, m sub j, can be from -j plus 1 to j, and therefore the degeneracy is 2j plus 1. For a linear molecule with a C infinite V point group, such as HCl, we have its three-dimensional rotational partition function as the sum of this exponential function times the degeneracy, 2j plus 1. Again, this is because the jth energy level has a degeneracy of 2j plus 1. We need to include all those 2j plus 1 degenerate energy levels into account. And then I'm going to approximate the sum with an integral, and I'm going to copy the lower limit here, 0, and upper limit infinity here. I replace j with x, and because j and x are dummy variables, and now I set z to be x times x plus 1. And therefore, we can simplify this exponential term to be negative beta times h bar squared over 2I times z. Again, z equals x times x plus 1. How about this 2x plus 1 times dx? This is simply dz. If you take dz over dx, you will get 2x plus 1. Therefore, 2x plus 1 times dx is simply dz. So we just need to integrate this exponential function. And then for simplicity, we will set u to be this whole thing. So this whole thing is u. And then we have this exponential function to be e to the power of -u. And again, u is beta h bar squared over 2I times z. Therefore, dz equals 2I over beta h bar squared. And then we can easily integrate this e to the power of -u, which is negative e to the power of -u. We plug in the lower and upper limits, and we get this integral value, which is 1. And then the result is simply 2I divided by beta h bar squared. And by convention, we introduce a b, rotational constant. And hcb equals h bar squared over 2I. So sometimes you see the three-dimensional rotational partition function expressed as 1 over hcb beta for that reason. Again, it's just for convenience, especially if you study the infrared spectroscopy of a linear molecule. B, the rotational constant, is defined this way. And now we're going to use this equation to compute the three-dimensional rotational energy. E equals -n times d ln q over d beta. So here we're going to use that equation. We plug in negative n and then d ln q. This part is your q or d beta. And this part can be expanded into the sum of two exact differentials. You have 1 over beta here, and then you have a second term, the exact differential of ln 2I over h bar squared. Fortunately, this part does not depend on beta. I is a constant, h bar is constant, therefore we just need to take this first derivative, and if we do that, we'll get n over beta in the end, which is also n times kBt. So the average three-dimensional rotation energy per linear molecule is simply kBt. So really, it's essentially a two-dimensional rotation, and each dimension give you half kBt. Two dimensions give you 2 times half kBt, which is just 1 kBt. And why it's actually a two-dimensional rotation? Well, because if you have a linear molecule, the rotation about its own molecular axis does not count. It does not count. Therefore, if you have a linear molecule, you have only 2 rotational modes, and then you have 3 translational modes. And then how about vibrational modes? If you have n atoms, you have a total of 3n motions, and then therefore the number of vibration modes is 3n minus 3 translation minus 2 rotation. You get 3n minus 5. So there's a difference between linear and nonlinear molecules. Linear molecules have 3n minus 5 vibration modes. Nonlinear molecules have 3n minus 6 vibration modes. Now, for a linear molecule with a d infinite h-point group such as H2, so H2 has an inversion center, and notice that we put a 2 in the denominator. This is called the rotational symmetry number or rotational symmetry factor. And why? This is because if you actually rotate this H2 180 degrees, you get the other permutation. These two permutations are identical because the 200 atoms are indistinguishable. So therefore, we have to divide the three-dimensional rotational partition function by 2. But this rotational symmetry number, although it lowers the partition function by a factor of 2, and consequently lowers the rotational entropy by kb times ln sigma. Sigma is the rotational symmetry number, but it has no impact on the rotation energy because, again, if you look at this expression of rotation energy, if you put 2 here, you simply just included a 2 here, and again, d ln 2 does not depend on d beta at all. Therefore, it has no impact on the rotation energy. However, in the expression of entropy, you do have a kb times ln q term, and then this symmetry number does play a role.